Welcome to Engineering Mechanics video lecture. In this video lecture, I am trying to explain you about kinetics of curvilinear motion. When the vehicle is moving from initial position to final position on the curvilinear trajectory, the radius of curvature of curvilinear path is considered as rho. When we wanted to find the kinematic parameters of moving particle which is in curvilinear motion from initial to final at P, we have to follow two methods. Why? Because velocity of moving particle in curvilinear motion of the particle is changes from point to point, and also direction of acceleration changes from point to point, so that we can follow either normal and tangent components method or rectangular components method. Now we can learn normal tangential components of kinematic parameters in curvilinear motion of the particle. At point P, the direction of velocity is directing tangential to the curvilinear motion of the particle at P. This indicates us tangential acceleration direction. Perpendicular to tangential acceleration through P, normal acceleration is directing towards the center of the curvilinear motion of the particle. The acceleration which is directing towards the center of curvilinear motion is considered as a centripetal acceleration. When the particle is moving from initial to final in curvilinear motion, opposite to the normal acceleration an, centrifugal force is generated. When the mass of the moving particle is m, we can estimate centrifugal force Fn as m into an. In the same way, opposite to the tangential acceleration at, tangential inertia force will be generated within the moving particle from initial to final. Inertia force generated within the moving particle opposite to the tangential acceleration considered as Ft. We can estimate that inertia force by following mass of a moving particle m as m into at. According to definition for the normal acceleration or centripetal acceleration of the moving particle in curvilinear motion is defined as it is proportional to square of tangential velocity and inversely proportional to the radius of curvature, so that we can write it as an equal to v square by rho. We can write tangential acceleration at as rate of change of velocity dv by dt. While we are applying dynamic equilibrium along normal direction and tangential direction, we have to consider all other forces. At the contact in between particle and curvilinear path, we have to consider normal reaction force perpendicular to the contact surface at P. and also weight of the moving particle which is acting downward direction also consider. While we are applying equation of dynamic equilibrium along a normal direction, the forces which are acting along the normal acceleration considered as positive. Opposite to normal acceleration, if any force is acting, considered as negative. The force which is acting along the tangential direction or tangential acceleration is considered as positive. The force acting opposite to the tangential acceleration direction is considered as negative. For this condition of moving particle at point P, we can apply two equilibrium equations. One is along normal direction, another is along tangential direction. So we can write it as a summation of all the forces along normal direction equals to inertia force along the same normal direction. Algebraic summation of all the forces which are acting along the normal direction considered as a summation Fn. It is exactly equal to centrifugal force MAN. This summation Fn includes normal reaction force and weight component force along the normal direction. In this case, weight of moving particle is directing towards the normal acceleration direction. So we can consider it as positive. And normal reaction force which is acting at P point which is there on the trajectory or curvilinear motion of the particle is directing opposite to the normal acceleration. So we can consider it as a negative. When you write it in the equation of dynamic equilibrium, we can get W minus N equal to MAN, we can get, where AN indicates us normal acceleration, AN equal to V square by rho. On substituting AN value, we can get W minus N equal to mv square by rho. From this equation, we can find normal reaction force N. Normal reaction force N equal to W minus M into V square by rho. By following this normal reaction force equation, we can say the normal reaction force decreases with increasing speed and becomes zero at the point of losing contact. When you apply equilibrium equation along tangential direction, we can get summation Ft exactly equal to MAT.